A belt is a loop of flexible material used to link two or more rotating shafts mechanically, most often parallel. Belts may be used as a source of motion, to transmit power efficiently, or to track relative movement. Belts are looped over pulleys and may have a twist between the pulleys, and the shafts need not be parallel. In a two-pulley system, the belt can either drive the pulleys normally in one direction, or the belt may be crossed, so that the direction of the driven shaft is reversed. As a source of motion, a conveyor belt is one application where the belt is adapted to carry a load continuously between 2 points. Standards for use. The open belt drive has parallel shafts rotating in the same direction, whereas the cross belt drive also bears parallel shafts but rotate in opposite direction. The former is far more common, and the latter not appropriate for timing and standard V-belts unless there is a twist between each pulley so that the pulleys only contact the same belt surface. Non-parallel shafts can be connected if the belt's center line is aligned with the center plane of the pulley. Industrial belts are usually reinforced rubber but sometimes leather types. Non-leather, non-reinforced belts can only be used in light applications. The pitch line is the line between the inner and outer surfaces that is neither subject to tension or compression. It is midway through the surfaces in film and flat belts and dependent on cross-sectional shape and size in timing and V-belts. Calculating pitch diameter is an engineering task and is beyond the scope of this article. The angular speed is inversely proportional to size, so the larger the one wheel, the less angular velocity, and vice versa. Actual pulley speeds tend to be 0.5 to 1% less than generally calculated because of belt slip and stretch. In timing belts, the inverse ratio teeth of the belt contributes to the exact measurement. The speed of the belt is speed equals circumference based on pitch diameter times angular speed in RPM. Selection criteria. Belt drives are built under the following required conditions. Speeds of and power are transmitted between drive and driven unit, suitable distance between shafts, and appropriate operating conditions. The equation for power is power equals times. Factors of power adjustment include speed ratio, shaft distance, type of drive unit, service environment, driven unit loads, and pulley belt arrangement. These are found in engineering handbooks and manufacturer's literature. When corrected, the horsepower is compared to rated horsepowers of the standard belt cross-sections at particular belt speeds to find a number of arrays that perform best. Now the pulley diameters are chosen. It is generally either large diameters or large cross-section that are chosen, since, as stated earlier, larger belts transmit this same power at low belt speeds as smaller belts do at high speeds. To keep the driving part at its smallest, minimum diameter pulleys are desired. Minimum pulley diameters are limited by the elongation of the belt's outer fibers as the belt wraps around the pulleys. Small pulleys increase this elongation, greatly reducing belt life. Minimum pulley diameters are often listed with each cross-section and speed, or listed separately by belt cross-section. After the cheapest diameters and belt section are chosen, the belt length is computed. If endless belts are used, the desired shaft spacing may need adjusting to accommodate standard length belts. It is often more economical to use two or more juxtaposed V-belts, rather than one larger belt. In large speed ratios or small central distances, the angle of contact between the belt and pulley may be less than 180 degrees. If this is the case, the drive power must be further increased, according to manufacturers' tables, and the selection process repeated. This is because power capacities are based on the standard of a 180 degrees contact angle. Smaller contact angles mean less area for the belt to obtain traction, and thus the belt carries less power. Belt friction. Belt drives depend on friction to operate, but excessive friction wastes energy and rapidly wears the belt. Factors that affect belt friction include belt tension, contact angle, and the materials used to make the belt and pulleys. Belt tension. Power transmission is a function of belt tension. However, also increasing with tension is stress on the belt and bearings. The ideal belt is that of the lowest tension that does not slip in high loads. Belt tensions should also be adjusted to belt type, size, speed, and pulley diameters. Belt tension is determined by measuring the force to deflect the belt a given distance per inch of pulley. Timing belts need only adequate tension to keep the belt in contact with the pulley. Belt wear. Fatigue, more so than abrasion, is the culprit for most belt problems. This wear is caused by stress from rolling around the pulleys, high belt tension, excessive slippage, adverse environmental conditions, and belt overloads caused by shock, vibration, or belt slapping all contribute to belt fatigue. Belt vibration. Vibration signatures are widely used for studying belt drive malfunctions. Some of the common malfunctions or faults include the effects of belt tension, speed, sheave eccentricity, and misalignment conditions. The effect of sheave eccentricity on vibration signatures of the belt drive is quite significant. Although vibration magnitude is not necessarily increased by this, it will create strong amplitude modulation. When the top section of a belt is in resonance, the vibrations of the machine is increased. However, an increase in the machine vibration is not significant when only the bottom section of the belt is in resonance. The vibration spectrum has the tendency to move to higher frequencies as the tension force of the belt is increased. Belt dressing. Belt slippage can be addressed in several ways. Belt replacement is an obvious solution, and eventually the mandatory one. Often, though, before the replacement option is executed, retensioning addressing may be successful to extend the belt's lifespan and postpone replacement. Belt dressings are typically liquids that are poured, brushed, dripped, or sprayed onto the belt surface and allowed to spread around. They are meant to recondition the belt's driving surfaces and increase friction between the belt and the pulleys. Some belt dressings are dark and sticky, resembling tar syrup. Some are thin and clear, resembling mineral spirits. Some are sold to the public in aerosol cans at auto parts stores. Others are sold in drums only to industrial users. Specifications to fully specify a belt. The material, length, and cross-section size and shape are required. Timing belts, in addition, are required that the size of the teeth be given. The length of the belt is the sum of the central length of the system on both sides, half the circumference of both pulleys, and d the square of the sum of the difference of the radii. Thus, when dividing by the central distance, it can be visualized as the central distance times the height that gives the same squared value of the radius difference on, of course, both sides. When adding to the length of either side, the length of the belt increases in a similar manner to the Pythagorean theorem. One important concept to remember is that as d1 gets closer to d2, there is less of a distance until it approaches zero. On the other hand, in a crossed belt drive, the sum rather than the difference of radii is the basis for computation for length. So the wider the small drive increases, the belt length is higher.